My intention today is to actually give essentially a career guidance class to you. What I'm going to do is basically show what I do currently today in Ireland, working for a space company, and then go back from there, step back a bit, and go back to when I was in primary school and into secondary school, and to kind of explain what I did on the way to get where I am today. So basically, if I just explain these first videos here that were on when you were coming in, I'll just play them again. I'll keep the volume low. Just this one here is one on the left is actually an F-16 show that was actually I attended in Florida, and it was just amazing to see the fighter jets that you'd seen on TV. And if you've seen any of these shows anywhere in Europe, they're amazing. The second video is actually a rocket that myself and a few friends of mine made. We then went to a big field and we launched it, and it was pretty cool just to make a rocket, literally just to fly up into the atmosphere. And the third image here is actually of Shuttle Atlantis, which the payload which I was working on got launched into space on, and I had the privilege of actually seeing that launch of Shuttle Atlantis, and actually another 3 shuttles as well when I was in Florida. So basically, today is going to be my story, essentially, and the reason for doing this is that to kind of let you know that if you have an ambition or if you want to follow a career path similar to mine, that basically, with lots of hard work and an interest in that area, it is possible. And my career in science, technology, and engineering didn't evolve overnight. It kind of started when I was young, little things happening, and the pinnacle of kind of my interest obviously came when I ended up working in the Kennedy Space Center. So basically, my first thing, let's go on to here. So currently, I work for a company called EnBio. EnBio have basically a technology, and their background is to the point is actually a medical device. They have a technology for actually coating some really odd structures like this metal component here, and this is actually a hip implant which goes into your hip if you get actually bone disease or if you have arthritis, etc. And their technology was quite interesting in the fact that it was medical grade. It applied to lots of titanium or metal surfaces, mainly titanium, and they also had applications for their slideshow's broken up. And they also had applications for other areas. And you can see here actually this is a process that we use. It's actually putting PTFE onto a screw. And PTFE is very, very interesting in the fact that when you put water on the surface, the water actually doesn't stick to the surface, and it turns out to be coming into a little sphere, like as you can see there. And the interesting thing about that is that you can actually use that surface then for many applications for water protection. So then that brings me on to the technology that they had here in Ireland was very suited to medical device, but they also thought that it would have been very interesting for other areas. So about 16 months ago, I joined the company with my experience and background in the area I'm in, and the area of interest that I seen this technology working was space, as you could guess. And the idea of this was actually use their technology to put a surface onto titanium surfaces for applications from anything from satellites to shuttles, whichever. So what I have here is a video basically of a satellite that is actually going through some extreme environments in our solar system. It's actually going to go orbit the sun and perform some scientific experiments. And one of the things about this satellite is that it incorporates a lot of extreme instruments that need to perform at very high temperatures if it's going to launch to the sun. So I'm just going to show this video here and it'll be an introduction of basically what we do at EnBio.
The Sun. It is the ultimate source of virtually all the energy on Earth. It's the dynamo that drives the weather, and its energy, fixed in simple sugars by photosynthesis, directly or indirectly fuels almost every living thing on our planet. Furthermore, practically all the energy we use to sustain our complex society has its origins in the sun's rays hitting the Earth's surface. Because of its fundamental importance to our existence, the Sun is a critically important subject for scientific study. Solar Orbiter, an ESA mission, in collaboration with NASA, has the objective of sending a spacecraft to monitor and observe the Sun, using a suite of advanced scientific instruments, and at a proximity never before achieved. Scientists hope to learn more about our home star, and in doing so, usher in the next era in solar science. After separation from the American Atlas launch vehicle, the Solar Orbiter spacecraft will travel along a highly inclined escape trajectory on course for the planet Venus. During the few months between Earth and Venus, the Solar Orbiter spacecraft will deploy and check out the instruments and subsystems required to complete the mission successfully. Upon arrival at Venus, Solar Orbiter will perform the first in a series of slingshot, gravity-assisted maneuvers, which allow the spacecraft to travel to the final operational orbit using much less propellant than would otherwise be needed. At its closest approach to the Sun, Solar Orbiter will encounter almost 13 times the solar flux received at the Earth, necessitating the presence of the heat shield on the spacecraft. The heat shield is conductively isolated from the rest of the spacecraft using discrete mounting blades, and is composed of a separate, highly insulating layer held above a support structure by brackets. Also included are feed-throughs, doors, and mechanisms which provide the required fields of view for the remote sensing instruments. The heat shield relies on being able to reject heat to cold space via the gap between the layers. However, it is not possible to keep every part of the spacecraft behind the heat shield. The solar arrays must be exposed to the Sun, and the high-gain antenna must sit in the sunlight in order to access the widely varying Earth positions. Accordingly, Solar Orbiter must manage the temperature of these critical items to ensure their survival as the distance to the Sun varies.
So basically that's an insight into Solar Orbiter satellite, and basically our job within EnBio, what we've done is basically we've produced a surface, a black surface it's called, that's allowed this satellite to basically perform its mission. And our black surface, which is a replica here, basically it's on a what you call a titanium foil, and I'm actually going to show this around to you if you want. And what our surface is able to do is that it's able to absorb the solar energy from the Sun. That satellite, in its closest approach to the Sun, is actually going to encounter 13 times what we get here on Earth. And that then means that the satellite's going to operate on the front of its heat shield at about 700 degrees. And then going towards the electronics of the satellite have to operate about 30 degrees, same as your ordinary your electronic device here on Earth. So what the idea of this heat shield, what it does is it protects the rest of the satellite from the intense heat. And then, interestingly enough, the back of the heat shield actually operates at about minus 150 degrees Celsius, due to the fact that it's in the shadow of the Sun. And this is really at an extreme environment that the satellite has to actually perform its experiments, it has to survive, it has to communicate back to Earth, and it has to actually, the mission, it'll take 3 years to get to the orbit close to the Sun, and it's going to have to last about 7 years in orbit around the Sun. So it's a very, very difficult mission to actually perform, and basically with the addition of our heat shield, it actually should be very, very interesting to actually make this mission work. One of the things about our surface is that we developed it from the medical, and basically we've seen the application in space, and it actually fitted very well. It was very, very, very similar to a medical device. Our coating it does not degrade. It doesn't interact with any of the extreme environments of space. And basically, same as the coating going into your body. When you put a coating into your body, you don't want it to actually interact with your body and cause problems. So it was very, very suited in that respect. And for the heat shield, also, the surface of the heat shield was one of the surfaces that we're interested in. The other surface we're interested in was actually a full suite of tubes and instruments that were actually going to be encapsulated within the solar orbiter. And these allowed actually instruments to actually look through the heat shield and into the Sun and perform their experiments flawlessly, we hope. So I'd just like to pass this around, just so you can so basically, just if you think about the size of the satellite, there's a small piece of foil just being passed around, and actually the size of the heat shield we're in the process of manufacturing is 9 square meters. So it's about the size of I don't know, a quarter of this room, we'll say, and it's a huge monster of a satellite that we have to actually make, and because of that we have new technologies that we have to actually introduce into our company. We need to actually employ lots of new engineers, new scientists to actually help us do this. And as well as that, then, as we progress with the mission for the satellite, our colleagues in the European Space Agency, the Spanish Space Agency, and the Italian Space Agency are actually always asking us questions: can we solve more problems? And basically, what they keep on asking us is, can we solve a problem? And our company now has diversified just from being a medical device company into a space company, and now solving more problems for our colleagues across Europe. My business colleague actually loves this slide. Since we're the surface that's actually going to be very close to the sun, he calls it the best surface under the sun. It's also going to be the nearest man-made object to the sun, and then because we actually control the temperature of the satellite, he says space has never been cooler. So I don't know if you agree with those statements, but it's very good. I'll open the floor to actually just general questions, anything you've interest. Ask me why my presentation is not working 100% if you want. Anyone interested? That's a good question. Not enough is the answer. Basically, I'll go through kind of what I've done. I've done a cert diploma degree in engineering, and I also did a PhD in engineering. And basically, what my experience and background and the education I've got, they're kind of very specialised. And in Ireland, there's 42 companies that work in space, and my hobby, my interest is space, and I want to work with these companies. And that kind of restricts me then to actually, they mightn't pay me enough, but, it's an interest I have, so I go work for them. So my point is basically, it's not the money that makes me do this. It's actually my interest in this area from very young up to now. And basically, money will come, hopefully, eventually, if we win these contracts and get our stuff on the satellite. Go for it.
Where will this satellite be launched?
Yeah, thanks very much. Basically, the satellite, it's a joint collaboration with the European Space Agency, which is based in Europe here. And Europe is actually making the satellite, so there's a number of European companies actually building the satellite. And one of us is going to be us, who are going to develop the heat shield. The rest of the manufacture is going to happen in Spain and Italy and some in the UK. Then that satellite, as a complete unit, will actually be shipped over to NASA. And NASA is our actually collaborative partner. They're actually going to launch it on a rocket called, what's it called? I can't remember. Delta IV, I think it is. It's a very large rocket. And basically, when I was actually in Florida, I seen 5 of these satellites launch, or satellite rocket launch. These rocket launchers are actually very, very big. They're not as big as the shuttle itself, but they're very, very big, and they carry very, very heavy payloads up to space. We're actually a relatively small satellite. Our satellite's about 9 square meters in size, but compared to military satellites and weather satellites, it's actually very small. But we actually are going on a very big rocket because we're actually going up to a very, very high altitude, and we have to get a very, very high escape velocity. We have to travel about 36,000 kilometers an hour as we leave the Earth, so we get to launch around the sun. So thanks for that question. Yes, sir.
How much did it cost to make it?
Yeah, that's a good question. Hopefully, it's all worth it. The Solar Orbiter program actually costs about 250 million to develop, to actually put it on a rocket and actually launch it. It's going to be delivering science, trying to understand the sun for the next, hopefully 10 years. and it'll actually see things about the sun that we've never seen before. It'll try to understand how the sun operates, why it gives off flares. If any of you were interested, actually there was a solar eclipse there in Australia. I think it was yesterday or the day before, and it was very interesting to see the solar eclipse with all the magnificent solar flares come out of the sun that you can actually see just when you're in eclipse. This solar orbiter, because of its instruments, can be very close to the sun and actually look at these and see why they actually happen, and try to understand them a bit better. So hopefully the investment of 250 million is paid off with the amount of research and work and jobs that it creates here on Earth. The science then it brings back then to hopefully understand better how the sun works. An example of that is, for example, solar flares can actually cause problems here on Earth. They can actually put out power grids. So if we could detect and preempt when one was going to happen, we could then design our power grid system to actually wouldn't interact with this solar flare. So that's just one outcome, but the science of understanding the sun is probably a major one as well. So any more, guys? And keep the questions coming, anything you want. So the next one is basically, how did I get here? And now I'm going to talk for about 10 minutes, and I hopefully won't bore you too much. Basically, kind of, from an early age, I've had an interest of asking questions and looking at things, how they work. And if you've ever seen Discovery Channel, How Stuff Works, that was basically me at a young age kind of going, how does whatever work? And I always had an interest of just looking up at the night sky, looking at stars, looking at the moon, kind of going, they're kind of pretty interesting. And, can we go there someday? Can we go back to the moon? Can we go to Mars? Can we or can we not? And that interest has always been there from when I was very young. And I just have a silly story. And it's called a TV incident. And then there's a do not try this at home. But when I think it was about 10 actually, and I was at home, and my parents were actually gone off, and I was bored. I was actually watching TV, and the question came to me was, how does a television work? What's inside of it? So daring as I was, I took the television apart, and there was literally lots of pieces around my bedroom, and there was lots of pieces of the television around. And my parents came home, and they came down to me, what are you at? And they seen this television in bits all over the ground, and they were going, what the hell are you doing? And I was here like, I'm just having a look. And they gave out to me, they grounded me, whatever they did. And so they said, sent me to my room, and they said, clean up the mess. And so about 2 hours later, parents are kind of after really giving out to me really bad, and they said, all right, we'll come down and see what he's up to. And I was down in my room watching TV, and it was the same TV I had taken apart, and they were kind of a bit surprised. So my point here is, don't take your television apart. But my point here is actually, there's ways of kind of asking questions and trying to understand stuff. And my point is, when I was very young, I asked those questions, and my way of actually trying to understand them was actually to investigate them, take things apart, look at them, and try to understand them. So that kind of, that carried through up into, we'll say, junior certificate. And after junior cert, I was lucky enough to actually get a job with a mechanic who didn't pay much, actually. My father always said to me he spent more money on petrol bringing me to the mechanics for me to work there than actually I was paid. But anyway, but I ended up working with this mechanic, and he was a great teacher, and he didn't just fix cars and stuff like that, but he also fixed lawnmowers, hedge trimmers, all the really small engines. And that was kind of a great experience for me to kind of understand that from a relatively really young age. And I ended up actually working for him for summers and weekends up until I was, 21 or 22. And it was a great interest I had. And in between that, then what I kind of learned was that the experience I was gaining from that really helped me in school, and really helped me in kind of answering some questions. And going into, I did actually transition year. I don't know if is there any transition years here today? No, you're the whole group. I actually did transition year after my junior cert, and what I kind of learned from transition year, Yusuf just started there this year, but what I kind of learned from transition year was actually, it was kind of a maturing time for me. I got new hobbies. I really focused in on hurling actually, and I liked that, and I kind of met new people. I was in a CBS actually, and we actually had some group meetings with the local technical school and the girls' school as well. So it was all a very new, interesting time to meet new people, and you know, your social aspect of life comes alive as well. But all in the background, my hobbies kind of, you know, gave time to do some hobbies and do some actually very cool subjects and projects during fourth year. From there then, went into fifth and sixth year, and I was kind of generally, you know, you might say a nerd, but anyway. But I liked biology, geography, tech and graphics or drawing, and physics. And I was in physics actually one day, and is there any fifth or sixth years doing physics? You doing physics? You learned about the cathode ray tube. Do you still do that? No. Well, it's basically part of it's, you know how the old television used to work, and it's basically a tube in it called the cathode ray tube. And I remember being in physics, and I remember being in physics, learning about this. And this was me after taking a television apart when I was 10. But still, I didn't really understand how the cathode ray tube worked. And my point was that when I was in school, I always tried to actually, you know, learning from books was one thing, but obviously relating it back to some experience or something that I did was always way better to learn. And from there then, I basically, in the sixth year, I ended up, you know, filling out my CEO form. And is there any sixth years here? Yeah, you're 6 years. You're going to fill out your CEO form, or if it's still called that, if you want to go to college, and basically, I filled out mine in a really, really odd way. I filled out, I went to veterinary first, then I was biology, then I was engineering, then aeronautical, then biology, and my career guidance teacher was going, James, please, you know, focus on one area, focus in on engineering or biology or something. And my point was actually, well, you know, my interest is kind of, I don't know what I want to be really, to be honest. And sometimes, actually, even today, I don't know what I want to be. And you know, I'm in an area that, you know, it's very, very general, and I can actually move in and out of different areas. And I was like that when I was in fifth and sixth year. And I ended up actually deciding that I wanted to go to college, and I wanted to then do engineering, because one of the reasons why I chose that was because I actually investigated. I went to some opening days in college. I went to some PLC courses, opening days. I went to different opening days to see what was going on, what I wanted to really do after school. So 6 years, or when you become 6 years, just go and investigate what you want to do. Go to the colleges that may interest you. Talk to lecturers, talk to students, and just find out in general what they tell you, and make up your own decision. And the whole idea then is to obviously, you know, do something you like, and that's probably the aim of this whole exercise.